integers and n is greater than k. Then if you put n balls into k boxes, there is a box with more than one ball.
Also, it's the pacifist version of the pigeonhole.
Yeah, so you stole my joke, right? I was going to say something about humane behavior and stuff. Okay, yeah, so we changed the names from pigeons to balls to protect the innocent or something. Okay, so let's go ahead and write down the proof of this, all right? Often in math, there are things that are completely obvious, but they're really hard to prove, right? This is not one of those cases. This is also completely trivial. So what do we do? Well, let's assume that each box gets less than or equal to one ball. All right, that'd be the opposite of this, right? So how many balls? How many balls are there? Well, we add up. There's less than or equal to 1 in each box. So there's less than or equal to 1 times the number of boxes. What was that? That was k. Right? And that's less than n. But on the other hand, we also call this number n. So we've got n less than n. This is a contradiction. There's my contradiction symbol, and so that concludes the proof. All right. Some of you may not really be happy with this formulation, so we could try it, version 2, using grown-up words, right? So let's say I've got a function from a to b, and the cardinality of a, right, the number of elements in a, is greater than the number of elements in b. Then, okay, what's the translation? So the elements of A are sort of like the balls, and the elements of B are like the boxes, right? So I'm sticking balls into boxes. So if more than one ball goes in the same box, that's non-injectivity, right? Then F is not injective, or one-to-one. Okay. So totally obvious, right? Getting a couple of board books maybe. That's a good thing, right? Everything's very clear. So I promised implications. So I've got 3 implications of the pigeonhole principle for today. Number 1. So this is in the field of hair growth. So I tried to look up on Wikipedia like the scientific name for scientists who study hair growth and stuff, and I couldn't come up with anything. So if you know this, I'd be interested to know what scientists are called that study hair growth.
Snake oil specialist.
Snake oil specialist? It's big business. Type in hair growth to Google.
I know there's a scientific term for having bald spots.
Oh, yes, I did find that out.
Yeah.
I forget what it is. Okay, anyway. So what's the implication for hair growth? So the theorem is in Atlanta, there are 2 people with the same number of hairs on their heads. Okay? Go down to Atlanta, go look around counting people's hairs, and you can verify this, all right? But probably easier not to do that, and to use our pigeonhole principle. Okay, so proof 1, go find 2 bald people. Right? This is the easiest way to prove this statement. I think there's probably 2 bald people in the Braves. If you know the Atlanta Braves, there are probably 2 bald people. Okay, so proof 1, find 2 bald people. They both have 0 errors. Okay, so let's amend the theorem. 2 people, not bald, with the same number of errors. Okay, now we've actually got to do this one. Well, let's write down a function. So I'm going to define f, and it's going to be from people in Atlanta.
Metro or city proper?
Metro. Thank you. Metro Atlanta. I don't really know what the difference is, but
It's 10
Somebody
factors.
all right.
It might make a difference.
So, well, maybe I don't want to put n there. I'll put it the set of numbers. Right. So what's the range for this? We said no bald people, so it's going to be 1 to some number n. We should think about what n should be. Okay, so we know what the pigeonhole principle is, and we know that we have to know the cardinality of sets to apply it. So, question 1. How many people are in Metro Atlanta? I'm sort of assuming that no one in Atlanta is bald here when I use this statistic. Okay, so I asked Alex, he knew. I asked John, he knew. Anyone else from the area that I can shame? Dr. Azov, you're sort of from the area, I guess. Well, I mean, living in the area.
I guess it's more than 1 million.
More than 1 million, correct. 4.5 times. Okay, so there are 4.5
That's like
million ish. All right.
500,000.
So now, what should n be? Right?
It's more.
Count your own head.
What? Yeah. So there's this German scientist who went around dead people and counted their hairs. Right? The kind of guy who goes around doing this for his free time. It's a strange thing. But he found out this is sort of interesting. So it varies a lot by hair color, and so at the high end, blondes, 140,000 average, and all the way at the bottom, redheads, 90,000. All right. So let's just be safe and say that, this is average. Nobody has more than 1 million. All right, that's just absurd. Having 10 times more hairs on your head than like a full headed hair. Head hair. All right, so this is safe. All right.
I don't feel that comfortable. There's some weird people out there.
I know. I had a great time planning this talk because I'd think of all these strange things and I'd go on Google and I'd type it in and then I'd just jump back. Like the hairiest person in the world. You type that in, and accidentally hit images and your wife walks in the door. Oh man. Okay. So.
Wait, your wife is the search result?
No. I got a medical supper for you. All right. Okay. So, since 4.5 million is greater than 1 million, there are 2 people with the same number of hairs on their head. This is non-injective, meaning there's 2 people get back to the same number. Right? And so you may say, well, can't we say something stronger? Because this isn't just more, this is like a lot more, right? So, of course we can. Right? So the so-called generalized pigeonhole principle is basically, the way I think about it is that you've got some data, something has to be at least the average, and something has to be at most the average. All right. So let me write that down in terms of all the boxes. If you put forget which one was in K, it doesn't matter. If you put n balls in K boxes, n greater than K, then there's a box with greater than or equal to n divided by K balls. All right, and the proof is the same. So what do? You say, well, if each box has less than n over K, how many balls total do I have? Well, I've got K times, or I've got less than K times n over K, so I've got less than n, but n is the number of balls I have. Same proof. Nothing of my sleeve. So what does that mean for Atlanta? What is the stronger statement? What's 4.5 divided by 1? 4.5. So there's 4.5 people, greater than or equal to 4.5 people. Oh, but you can't cut people in half. That means there's 5 people, in fact, in Atlanta that have the same number of pairs in there. They could go form a club and like be a basketball team or something. Okay. So that's all I have about hair growth. Okay. So implication number 2. This is to let's see, inbreeding, or I think incest has sort of a negative connotation.
And inbreeding doesn't.
I've got like my best friend from Kentucky. So. Okay, so I need a volunteer for this. I need a volunteer for this. Who's going to volunteer for the example of inbreeding? Yeah. I'll just pick Eddie if no one raises their hand. Okay, Eddie, great.
All right. Well.
No, you don't have to move. You don't have to move.
He meant Eddie Azoff, actually.
I say I was
Okay. No. I'm just going to use your name.
All right. Right on.
Okay, so the theorem is Eddie, it's IE, right?
Yes.
Eddie's family tree in graph theory terms is not a tree. It has a cycle. Okay, so I guess another way to say this is he's got some ancestor, maybe his great-great-great-grandmother, whose parents were related. Okay, they were 15th cousins. It happens. So let's prove that Eddie's family tree is not a tree.
Depends if you believe that all humanity came from Noah.
No. This is not depending on any
Religion-independent proof.
creation, personal creation beliefs or anything. Okay, only the pigeonhole principle. We can all believe in the pigeonhole principle. All right. So how's the proof go? Well, let's draw Eddie's family tree. So here's Eddie down at the bottom. There's mom. There's dad. Grandma, grandpa. And we've got the greats, great grandma, great grandpa. And it keeps going. Right? This is what a family tree is. So, this is sort of too broad. So I'll say in the last 1,000 years. We don't have to, trace it back. There weren't humans like some number of years ago. Okay. So the function I want to make is from dots in the family tree to the set of people who ever lived on Earth. Right, so this is some dot. This is your great-great-grandma. And we go over here. She lived on the Earth at some point, so we go find her. Okay, that's how we do that. Easy? Okay, so what's the cardinality? I'll call this set A and this set B. So what's A? What is cardinality of A? Well, let's see. We won't count Eddie, so it was what? It's 2, that's the parents, and then 4 for grandparents, and then 8. And we keep going. And, well, let's say 25 years a generation, 40 generations. 40 generations. So what is the sum? Well, it's 2 to the k from 1 to 40. So what is this? Well, I guess it's 2 to the 41 minus 2. You guys know how to count this up, so it's not that big of a deal. Here's 2 to the 41. Whoops. And so here's half. That's 2 to the 40. And then half of that, this is 2 to the 39. And then half. So you just keep getting half. What do you leave out? Well, you leave out 2. There we go. All right. So I wrote this number down. It's fun to write really big numbers. 2199023 25555. Pretty big number, right? Okay. So now we've got another fun statistic. How many people ever lived on planet Earth?
110 billion?
Somebody said something?
Was it 110 billion?
Yeah, man, that's impressive. So I have 100 to 115 billion. That's the range. How did you know that? That's amazing.
Some article I read.
Oh, cool. All right. Well, I feel really confident. So 100 to 115 billion. That's the cardinality of P. All right. Is this bigger than? Let's see. So thousands, millions, billions. This is like 2 trillion. All right. So since that number over there is bigger than this number right here, this map is not injective. I mean, some of these dots are the same. Right? We got to take this graph and we got to identify some of these dots. Right? That's going to make a cycle. Right? This tree is not a tree.
Actually, by the corollary, that would mean that one person roughly serves 10 different functions in that tree.
You know, I had the same thing. I was like, oh, generalized pigeonhole principle, and I thought I don't want to know what that is. I don't want to think about that. You know.
Oh wait, that's a lot more than 10.
Yeah, it's a lot. So, well, let's just not think about that. The Royals used to keep it in the family, right? It was cool. Right? So let's not think.
If you just did this for 2 generations, it would be upsetting.
Maybe we shouldn't delve too deeply into these matters. Okay, so these were sort of silly and fun. Well, maybe not that fun. Maybe silly and disturbing. So let's get serious. I promised you 3 implications of the pigeonhole principle. So, number 3. So this is going to be meaning of life / maybe existentialism. All right. So we're going to start with the math. and we'll go figure out the meaning of life after we do the math. Right? Okay, so what's the math? Well, I'm going to state this theorem. And there might be some words in here that you don't know, but we're going to define them. That's not good. Okay, so this is called van der Waerden's theorem. Van der Waerden. I think that's more or less right. Okay, and it says if R and K greater than 0 are integers, then there exists an integer. The integer's got a long name. It's called W of Rk. It's greater than 0, such that if you color the numbers from 1, 2, 3, all the way out to W of Rk. Alright, so color means exactly what you think. We just go over here and we color it purple or orange or yellow. Alright. What happens? There's a cliffhanger. I should say how many crayons are in your box. You only get our colors. Color these numbers with our colors. Then there exists a monochromatic. Monochromatic is just what you think, all the same color. Arithmetic progression, I'll tell you what this is, of length R. Did I say R is the number of colors? I think I want K to be the number of colors. Okay. So this number is going to depend on R and K. That's why we write W of RK. Okay, so the definition of an arithmetic progression. So it's just going to be some subset, a subset of the form. So there's going to be some number, and then we add b to it, and then we add 2b to it, and we keep doing that. And we want it to have length R, so we add b to it, R minus 1 times. Alright. This is pretty easy, but I'll just write down a couple so we're all on the same page. So let's do a little again. Let's say we take the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's color with 2 colors and see if we find an arithmetic progression. So what do you think? I'll color the first one. What do you think? 2. Maybe switch it up to orange. Maybe keep it orange. Maybe go back to blue. Keep it blue. Who knows? So here's some coloring of the numbers from 1 to 10. So is there a monochromatic arithmetic progression?
Sure, what length?
Ah, very good. What length? So, an arithmetic progression of length 1, that's pretty boring, right? Just 1 number. What about length 2? Also really boring, right? These 2 are an arithmetic progression. You add 1. So are these 2. We added 3. Right? So length 3 is sort of a, oh boy, length 3 is sort of the easiest case. So do we have length 3 again? Let's see. 1, 4, so we added 3, so we add 3 again, we get 7, no. Maybe 2, 3, no. 2, 6, we added 4, 10. Hey, look at that. All orange, we added 4 and then we added 4, right? Are there other ones floating around?
159.
159. Okay, cool. So, does this mean that W, let's see, this is going to confuse me all the time. Length 3, 2 colors. So does this mean it equals 10? Well, I didn't say this, but I want this to be the smallest number. Well, we don't know. Maybe this number is way bigger than 10. We just did a stupid coloring. Right? Maybe there's some clever way to color the numbers 1 to 10 such that there's no arithmetic regression. Okay? So we really should prove that that these numbers exist. Okay? That's why this is a theorem, not like an obvious thing, somebody said. So let's prove it in this case. So proposition W 232 W 32. Well, I'm going to give it some bound. Great job, Joe. Didn't write down bound. Okay, let's say 5 times 65 is what I said in the lounge. Hopefully that's right. 65 times 5. 325. Okay. All right. It's always fun when you remember the proof but you don't remember the statement. This will happen to you as you get older. Okay, so how are we going to do this? Well, it's probably going to involve the pigeonhole principle and stuff, right? So if we take the numbers 1, 2, 3, 4, 5, blah, 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 out to 325, we can break them up into boxes of 5. So there's the first 5, second 5, third 5, you keep going, right? So I'll give these little labels. 1, 2, 3, and this guy is 65, yes. Very nice. Okay. So what am I doing with all these numbers? I'm coloring them in some way. There's some coloring that somebody handed down from on high. Upwards. Okay? So by the pigeonhole principle, there are 2 blocks in the first 33 blocks that have the same color. Well, why is that? How many different colorings are there of a 5-element set in order like this? Well, there's 2 choices for each number, right? And there's 5 numbers, so 2 to the 5. That's
31.
8. That's it. 2, 4, 8, 16, 32. Yes. Somebody was right. Okay. So I've got 32 possible colorings, and I've written 33 of them. That means one of them is repeated. And the map's sort of going the other way in that direction. I map each block to a coloring. There's 33 blocks and 32 colorings. So 2 of the first 33 blocks are the same color. So, like the same pattern, I should say. So I'll write those down. Let's say it's b1 plus 1, b1 plus 2, b1 plus 3, b1 plus 4, b1 plus 5. That's the first block. And then the second block, somewhere down the line, b2 plus 1, b2 plus 2, b2 plus 3. You guessed it. Alright. Okay. So they've got the same coloring with two colors, again by the pigeonhole principle. Of the first three, two of them have to be colored the same color. Alright? So what do we think? Maybe it's these two are the same color. Right? This block is colored the same, so it also looks like this. Right? If this was purple, we'd have our arithmetic progression already. Boom, boom, boom. So let's just say it's colored. Right? Okay. So presumably, I'm going to construct an arithmetic progression. Well, what's the magic? I'm going to look at further down the line, going back upstairs. There's some b3 plus 1, b3 plus 2, b3 plus 3, 4, and 5. Okay. And what do I want b3 to be? I want it to be the thing so that this is an arithmetic progression. So b3 is, well, what did we add to get from here to here? b2 minus b1. So it's b1 plus twice b2 minus b1. Alright, and so that's some block sitting out here. We picked this how we did, so that this was less than 325 right here. You can check that if you like. Nothing tricky going on. Alright, so the question is, how is this block colored? Well, this is an arithmetic progression. Well, maybe I should say it differently. What color is this block right here colored? Well, it's certainly not purple, because this one, this one, this one would be monochromatic arithmetic progression. Right? So I'm adding b2 minus b1 plus 1. Boom, boom. So it's not purple. Well, could it be orange? Maybe. All right.
You might be in trouble there.
I'm in trouble, Alex thinks. Well, what about b3 plus 3? b3 plus 3 better be orange. Because that would be an arithmetic progression. What about b3 plus 1?
Okay.
That better be an arithmetic progression.
You just took more steps.
Ah, I took more steps. Okay. I'm taking the long view. All right, so that means any coloring you throw at us, well, there we go. There's your monochromatic arithmetic progression. And so the proof of the general statement, I mean, there's...
Wait, I'm sorry, I missed a step. Where's our arithmetic progression?
Well, it's right here.
Oh, okay, those three. All right.
I mean, there's sort of this long argument of this can't be that, and this can't be this, and so this has to be that. We've got it on film now. All right, so the proof of the general statement, the Van der Waerden theorem, I mean, you've got a lot more stuff to worry about. You got to do like this double induction, but somehow this is like the essence, right? That your main tool is the pigeonhole principle, and that's kind of what gets you there. So maybe talk a little bit about kind of the field of mathematics that this is in the direction. So what's known about these numbers? What's known about W RK. I should just remember it's not in alphabetical order, and K goes with color. Okay. All right, I will tell you the state of the art of these numbers, because there's not a whole lot. I wouldn't defend anyone with that. Okay. All right, so we know that W32 is 9, W34 is 76, W33 is 27, W52 is 178, W42, I guess this is in no particular order, is 35. And that's it in terms of actually computing these. Is that amazing?
9's a pretty far cry from 325.
9's a pretty far cry from what?
The proposed bound of 325.
Ah, yes, yes. We'll get to how bad we are at bounding these numbers from above. Right? There's a novel we could write about that. Okay. So maybe a couple of remarks. So why is that it? Well, so when I heard about this, I was an undergrad when I heard about this, and I got all excited because I got to go to the University of West Georgia for the summer, and we were going to work on this problem. I'm like, man, you know, we got our new blue jeans on, and like we're just going to take this thing down, right? And I was like, well, let's just tell a computer to do it, right? Computers are good at this sort of thing, right? So what's like the easiest thing that's missing? Maybe 335. W35 is not on there. So how many things would you have to check?
22 5.
25 is not on there?
But the two length
So
progression is easy.
25,
Oh,
yeah, like 2 arithmetic progressions. Yeah, I didn't write
Yeah.
the ones with 2's in the first slot, or with 1's in the
6.
second slot. Okay, so what about W35? So what do you think it's going to be? 3-4 was like 76, and 5-2 is maybe it's around. It's probably greater than 100, probably. If you wanted to check all the 5 colorings of the numbers 1 to 100, right? So you go through. Each number has 5 options. There's 100 of them. All right. So you want to check all these colorings. This is about number of atoms in observable universe. And I was reading about this in how big this number was in a book, and it was something like if there were 1 trillion cities, and each city had 1 trillion computers, and each trillion computer labs, and each computer lab had 1 trillion computers, and each computer did 1 trillion computations per second, which apparently isn't that fast, I guess. This would take you something like 250 million years if there were 1 trillion Earths. So the point is, we have to be clever when we're thinking about these problems. Right? You hate it, and you have to be clever. Well, the good news is there's lots of stuff you can go work on, right? If you're bored tomorrow afternoon and you decide you want like an honorary PhD from somewhere, well, just go write down one of these interviews. Okay? Not that big of a deal. Okay.
Supposedly it only takes you a year to justify it for the Clay Mathematics Prize, so people can't break it in a year.
Yeah, I don't know that this is a Clay problem. I do know that, okay, well,
It isn't, but-
the thing I'm about to say, Ron Graham's offered $1,000 for it. Alright, so, whoopee, $1,000, right? Can't do anything with $1,000 these days. 20-minute phone call, maybe. Yeah, but that's some good change. So what about bounding WRK. Right? I don't really know anything about bounding from below, but we're going to talk about bounding it from below. From above. Alright, so Alex always likes to say this when he's talking about bounds. It's the current world record for an upper bound is 2 to the 2 to the k to the 2 to the 2 to the r plus 1. So this was a world record holder, Timothy Gowers, Fields medalist. He's a smart guy. So
In part for this.
That's what he goes for.
that's what he got it for?
Yeah.
We're giving him away now, right? Line up, get your Fields medal. No, but I mean, this is a large number for in general for K and R, and this number is much smaller than the number you get from running the proof. This whole pigeonhole principle, right? So this is a vast achievement. Okay, so that's sort of the and you get $1,000 if you improve this bound. Okay.
I don't have to give up.
Or maybe $1 million for another field.
Or maybe a million Fields medal, wherever you want. Walk around, realize that no one knows what you're talking about. Okay, so the last remark. So this was supposed to be about the meaning of life. This last little thing, right? So I've heard sort of this Van der Waerden theorem stated as follows: truly random behavior doesn't exist. Right. So this is what you do. You get your really sophisticated camera, all right, that takes a picture of the universe and doesn't leave anything out. Okay. So every second you work the camera and you get some picture. So the first second you take some picture, second, third second. The point is, if your camera isn't completely perfect and can notice every little minute detail, you're going to get patterns in the universe, right? So this is like Friedrich Nietzsche's big thing. Everything that happens in the world is going to keep happening over and over. So now we've got our mathematical proof that things in the universe are going to keep happening all the time. You guys are not nearly as impressed as I was. This deep interpretation. Okay, that's all I have to say. Does anyone have a question? Eddie?
Do you get to use the Van der Waerden theorem or the pigeonhole principle on a semi-regular basis when you're in the work that you do? Or when was the last time you got to invoke one of those?
So it'd probably be better to ask Neil and Alex. They sort of are a little closer to this type of work. What would you say? Maybe you don't have to answer.
I would say use the pigeonhole principle every other time I do something.
Every other time.
All the time.
I mean, it's also such a...
Going one from another, yeah.
Absolutely.
It's sort of... I used to... So when I was an undergraduate, I really wanted to do combinatorics when I got older. And I kind of realized, I learned the pigeonhole principle, and I was just so smitten with it. I was like, oh man, there's got to be great things like this all over the place in combinatorics, right? And I sort of got a little disillusioned because it seemed like the pigeonhole principle was the key proof in all these things. So I said, well, maybe I want a branch where there's a little more in terms of number of theorems. But quantity or quality, right?
Right. So if you're doing the proper mathematics with more continuous things, the dimension counting argument does the same job, right?
So yeah. So trying to think think of a good example.
So it's like if we take something that locally, or that looks like a plane, that's sort of flat, we want to map it continuously down to something that looks like a line.
Mm-hmm.
We're not going to be able to do this injectivity.
Yes. Somehow 2 is bigger than 1 is important here.
Right. That's
Wait,
key
in
fact
what
that
sense? Linearly or?
Continuously.
Sure.
Yeah, so then you get a lot of
Okay.
self-simulations.
But you
of
need
planes.
some sort of structure. You
Yes.
certainly
Well,
can
to
do
talk
it.
about dimension, you need
Yeah,
some sort
okay.
of structure.
Yeah.
And because the cardinality argument doesn't do it, right? Cardinality is stupid. We talked about this before. And I talked about it last time.
Right, because in, I forgot what class we were in. Oh no, this sounds like real analysis. That we made an argument for why R2 and R had the same number of elements in it.
Sure.
We did that, right? I'm
That's so this is a basic set theory argument, right? If you have 2 sets of infinite cardinality, then the product set, the thing that you get by whose elements are pairs of elements, so 1 from each set, has the same cardinality as the 2 sets that you started with. So, for example, the plane is the product of R cross R. The point on the plane is given by a pair of real numbers.
Right.
So it has the same cardinality as the real numbers.
I just said that.
Yeah, like, I was
I think
agreeing
the
with
point,
you.
I think the point is that
But it's
the
a very
result of
general
that
theorem.
is
I mean,
a lot less
it's-
significant.
It's the same theorem as saying that there are countably many irrational numbers, right? Because a rational number is given by pairs of integers. And
Right, but we're-
and many integers.
Now we've lost the pigeonhole principle, but like we were, okay, let's rewind. What you said at the beginning sounded like something that violated real analysis about a week ago.
Right. So
But he said
what you were saying
continuous.
was, as sets, these things have a map between them that's like 1 to 1 and onto if you want.
Uh-huh.
Right? But if you think about them topologically, if you try to do that map, you're going to be ripping things apart. It's going to be a very strange looking map. You'd have to do something weird, like say if you had 2 points and you have decimal expansions for them, you can interweave the digits of the decimal expansions or something ridiculous like that.
Maybe it's safe to say, if you're doing other mathematics and you don't think you're using the pigeonhole principle, you're probably just not realizing it. It's so basic a thing that, it's like tying your shoes.
So Joe, since you're writing bounds for Ramsey numbers, there was a really good theorem from the end of last year, which you could phrase in this language.
Okay, lay it on
That's-
me.
So, okay, you used K for colors, right?
Uh-huh.
So W3K, it basically amounts to that it's less than or equal to, let's say 2 to some constant times K.
Oh yeah, I heard about that.
That was by a guy named Tom Sanders from Cambridge.
That's fantastic.
That's basic. More or less. Maybe there should be a K log K or something.
Definitely an improvement. Yeah, so there's all sorts of subcases you could look at. I spent a long time looking at so-called generalized arithmetic progressions, because those weren't sort of too restrictive in some sense. So like instead of adding you can fiddle what you mean by arithmetic progression. You can sort of fix, well, I just want to think about 2 colorings, or I just want to think about arithmetic progressions of length. This. And there are lots of easier cases you can look at, and there is stuff known in some of these subfields. It's not as bad as I.
I also feel a little good about you saying that there's this small theorem base in combinatorics, or like after the pigeonhole principle, there's not that many names out there. That's, I think, where you can get some of your fame, by creating new names. like you mentioned van der Waerden's result. Well, there's a fancy result of that variety you probably run into called Hales-Jewett, which effectively says any tic-tac-toe game, if you bump it up to a high enough number of dimensions, is impossible to draw. No matter how many symbols you're allowed to use to fill the board.
I suppose I mean in
Okay, the dimensions is a function of the number of symbols you want.
so there's not the startup cost in combinatorics as there are in. So you know, if you want to learn, if you want to dive into research level algebraic geometry or something, you're going to spend a while.
Your dive is going to take about 10
The
minutes.
dive is going to take a long time. Whereas this, I mean,
Gravity doesn't work well.
I told you guys a bunch of problems that if you could figure out, you know, you'd be hot stuff, right? High five in the hallway. Blah, blah, blah.
It only took you an hour to use.
And it only took me an hour, right? So somehow this shows a lack of being built up into this guy, which is good to know. Thanks for everyone's attention.